In this lecture, we are going to take a pretty big departure from what we've been doing, and we are going to take Maxwell's equations and express them in Fourier space. We've been in real space, meaning we have x, y, and z. When we Fourier transform Maxwell's equations to go into Fourier space, we no longer have x, y, and z, we have something else, and you'll see we have weights on plane waves. Now, this is different than Fourier transforming Maxwell's equations to go from time to frequency domain. Here we're Fourier transforming x, y, and z to go from real space into Fourier space. So there's actually two types of Fourier transforms we could do. We can Fourier transform Maxwell's equations to go in the frequency domain or into Fourier space, or both, and we can have them in any combinations. This lecture we're going to be in the frequency domain and in Fourier space. So I want to give you a picture of what Maxwell's equations is in Fourier space so we can try to be intuitive about this. Then, like before, we're going to write Maxwell's equations in matrix form, but now they're the Fourier space versions. But this will parallel what we did with real space. When we Fourier transform a point-by-point multiplication, we have a mu times at h and an epsilon times at e. Point-by-point multiplications become convolutions. So suddenly, in Fourier space, we're going to have matrices that perform convolutions, and they are performing convolutions in Fourier space. So in addition now to diagonal operators, what you'll see, we'll have a wave vector matrix that's diagonal. We're going to have convolution matrices. We won't need our derivative matrices, but it serves a similar purpose. Then I want to talk about a technique called fast Fourier factorization, and this fixes a convergence issue that happens at discontinuities. Then I'll end with discussing some consequences of analyzing devices in Fourier space. It buys us efficiency for many devices, but it can hurt us for others, and it's important to understand that. Here we go. So what is Fourier space? We've been working in real space, and we've been drawing our grids with something like this. In real space, we know the field at discrete points, and we store these in an array, and we can look at them and visually already kind of see what the field might look like. In Fourier space, we don't do that anymore. In fact, we represent the field as a sum of a whole bunch of plane waves, all at different angles. And that's what I'm trying to draw over here. Now, while I have these plane waves drawn at physically different locations, they're not. They're all overlapping. They're of infinite extent and overlapping. And so instead of storing the field at discrete points like in real space, we store complex amplitudes for all of those plane waves. And the ability to do this comes out of Fourier theory. So Fourier space does not mean frequency domain. We can talk about Maxwell's equations in Fourier space and still have them in time domain or frequency domain. Fourier space means we've Fourier transformed x, y, and z. Frequency domain means we've Fourier transformed t, the time parameter, to get the frequency. So there is a difference, a big difference. One of the things we're going to use is the complex Fourier series. So here's a review of the complex Fourier series in one dimension, which you probably have seen. And now in this course, you've been introduced to the complex Fourier series in 2 dimensions. There's also a complex Fourier series in 3 dimensions, and in fact, any number of dimensions we want. We live in a 3-dimensional world, so we don't need to go past 3 dimensions. I do want to deviate for one moment to generalize this. This is not something we're going to do in this class, but I want to point this out. Using the Fourier transforms on the previous slide, we've essentially assumed a crystal symmetry where the principal axes are all at 90 degrees with respect to each other. So that means orthorhombic, rectangular, tetrahedral type of things. None of the others can fit into that mold. Well, it turns out we can generalize these complex Fourier series to account for any crystal symmetry that there is. So given lattice vectors, we'll just look at the three-dimensional case, given our three primitive lattice vectors, T1, T2, and T3, and these will be for the reciprocal lattice, by the way, so these are reciprocal lattice vectors, we can write a three-dimensional complex Fourier series this way. And we can do any crystal symmetry. Now in this class we're going to assume orthorhombic or better symmetry, and our lattice vectors will reduce to this, and in fact our complex Fourier series equations reduce to what we had on the previous slide. But I wanted to point that out. Just like all the methods, we're starting here in Maxwell's equations. This comes from lecture 2 or 3 where we were preparing Maxwell's equations. A lot of assumptions went into that. One of them being isotropic. Notice we have just mu r's here and epsilon r's. We're not retaining the fully anisotropic tensor. So that's our one big approximation. We can certainly handle that in Fourier space, but it involves a little bit more work, so they're not here. And a reminder that we have normalized the magnetic field according to this. We have the negative j here for convenience. Notice both sides of the equation don't have that j omega, and the one side doesn't have a negative where the other doesn't. Everything's positive, and we have a k naught sitting here. So the minus j is for mathematical convenience. This is for numerical stability, where we scale the magnitude. So we're essentially multiplying the magnetic field by the free space impedance to normalize it. So in 3 dimensions, we can expand our materials, the epsilon and mu, into these 3-dimensional Fourier series. And we can also Fourier transform our fields. So this top expression is the Fourier transform of the electric field. Now, we can take this expression, this general 3-dimensional complex Fourier series, and we can write it in this form in terms of 3 wave vectors. And these 3 wave vectors are related to the original beta and reciprocal lattice vectors through these equations. Or we could just write it as one vector equation. So really, our field is the sum of a bunch of plane waves, all at different angles with respect to each other. And recall that original picture. So that's why we can do that. And the actual spreading of these plane waves is consistent with the symmetry of the lattice because we have the reciprocal lattice vectors in here. So here's a summary of all of the expansions of the fields, how we're going to write them. So in place of the electric fields, the amplitudes of these plane waves we'll call capital S's, and there'll be an SX, an SY, and an SZ. And we have 3 dimensions. Our indices are P, Q, and R. So this S will be different for every combination of P, Q, R. So we just write that there to remind us of that. And this, the subscript X means it's the X component of E. And these just repeat. So we have X, Y, and Z for our S's corresponding to the amplitudes of the electric fields, and X, Y, and Z component, capital U's, which correspond to the amplitudes of the magnetic fields. And abandoning now the capital T1, T2, T3 reciprocal lattice vectors, now we're going to just handle the orthorhombic, tetragonal, cubic type symmetries, where the principal axes are at 90 degrees with respect to each other, and our wave vectors reduce to this. And this should remind us of when we're looking at periodic structures, those are our expansions that we use for calculating reflectance and transmittance. Same thing. Okay, so let's look at our first of Maxwell's equations, or our first scalar equation that we pulled out of Maxwell's equations. And we have these complex Fourier series expansions. And if we substitute those into this equation, just doing the blind substitution, we end up here. And this is very big and ugly. And so now we need to do some algebra on this, and we're going to do this one term at a time. We'll handle this first term, then the second term, and then this last term. Notice this last term is the product of 2 triple summations. Okay, the first ugly term. We are going to bring the derivative operator inside the summation. We can do that. This uz is constant. It's not a function of y, so it can come to the outside of that derivative operator. So the derivative operator is just operating on this exponential. And of course, we have, when we take the derivative of this complex exponential, we get the complex exponential plus, in this case, a minus jky for the PQR harmonic. Why the ky? Because we were taking a derivative in the y direction, and the only y variable was multiplying the ky. This is essentially a dot product of k dot r, where r is position. So we have our original expression again with this minus jky sitting to the outside. So it shouldn't be much surprise then, when we have a derivative in the z direction, we bring that to the inside, and we end up with a minus jkz multiplying our original argument of the triple summation. Now the last term, and a very critical term. We have the product of two triple summations. This is not one summation inside the other summation. This is the product of two triple summations. Well, there's something called a Cauchy product. And when you have the product of two summations, you can write that as a summation within a summation. So here's the outer summation, and then here's the inner summation. So that's exactly what we're going to do. So if we apply this Cauchy product rule to the product of these two triple summations, we can now write it as a triple summation inside another triple summation. And we'll call this the triple summation on the inside a p prime, q prime, and r prime, and that's to differentiate it from the p, q, and r on the outside. Now we want to pull everything together. This top equation is when we just did our blind substitutions. Then we did some math on each of these terms, and if we plug all those expressions back, we get here. Now what we can do, we have the same triple summation on the outside of all these terms. We can pull the entire equation inside that first triple summation. So this is everything left. Now what we have to realize is that this expression on the inside has to be satisfied for every combination of PQR. So in fact, let's just write this equation all by itself. And we end up here. Now we see we have a common exponential term. Sitting here, it's sitting here, and it's also sitting here on the right-hand side of the equation. So we can divide by that and cancel that. And here's where we end up. And in fact, we could call this that particular Maxwell's equations in Fourier space. Here's an alternate way to derive it that adds a little bit of intuition. So let's say we start with this original Maxwell's equation, and we Fourier transform this. What we'll see is we get the minus jky's multiplying the hz's. And this, that we know is a point-by-point multiplication, when we Fourier transform a multiplication, guess what? That becomes a convolution. Well, hey, remember that weird triple summation thing? The product of two triple summations, and we ended up with a triple summation left over? We actually know what that is now. That is a convolution. And we're in Fourier space, so this is representing a convolution in Fourier space. These A's, these A coefficients come from the FFT arranged into our Toeplitz convolution matrix. And so we're convolving, if you will, the FFT of epsilon with the FFT of our EX field, our electric field. So that's what's happening here. So if we do this with all of Maxwell's equations, and we have 6 of them because we took the two curl equations and expanded them, and we apply all this algebra we just went through, here's where we'd end up. And this really is Maxwell's equations in Fourier space. And of course we could write them in a slightly different form this way, using our direct sort of Fourier transform, and we see that we have these convolutions on the right hand side, which isn't necessarily apparent looking at our previous equations. And a reminder of how we defined our wave vectors. So what does this look like? So we have this huge expansion over P, Q, and R. So we have a whole bunch of plane waves that can scatter out in all three dimensions. So if I look at just a limited set of them, here's what they look like. All these different angles. Now, as I mentioned, I'm drawing these at physically different locations. That's only so we can see all of them. In fact, they're all overlapping. So a more accurate picture would be this. And in this volume of space where all those plane waves are overlapping, that's where we reconstruct our periodic field. Now, this big tangled mess of plane waves, to me, is rather confusing. It's maybe a clearer picture, but what we have on the left, I think, shows the full span of the wave vectors much more clearly. So we derived Maxwell's equations in Fourier space, and I mentioned that each one of those equations has to be satisfied for every combination of PQR. So in other words, for every spatial harmonic in our expansion, we write each one of those equations. Well, now we have a large set of equations again that we want to write in matrix form. So let's look at how that's done. So here's our equations, just to remind us. And I'm writing these to be a little bit more compact rather than write the summation form of these, but it's the same equation. And we'll look at this first equation. This equation needs to be written once for every possible combination of P, Q, and R. And here's how we're defining P, Q, and R. We always have an odd number of harmonics along each direction. So we'll call this first direction X, and we'll define a capital P. So these are integers that go from minus P through 0 up to positive P. So for example, this might go from minus 11 all the way up to positive 11. So the total number of harmonics in our expansion is this. We have 2 times this capital letter P or Q or R, but we're adding 1 because we pass through 0. So we have a lot of harmonics, potentially. Now we want to jump to matrix form. So we write our original equation of Fourier space, but now we have the triple summation. And this large set of equations would look like this. Here's our final equation in matrix form. So these are the same equations, just this is the assembly of all possible combinations of P, Q, and R. Now let's look at what each one of these matrices look like. Well, this is a constant, ky, for each value of P, Q, R. So it's really doing a point-by-point multiplication here. So in fact, this K term here becomes a square matrix, capital KY, which has all of the KY components running down the diagonal. In this case, the I subscript is either X, Y, or Z, depending which one we're talking about. And so they run down the diagonal. And zeros everywhere else. So these K matrices are very fast to calculate. We calculate all of the wave vector components and then throw those components into diagonal matrices. Well, the column vector U sub I, so again I is either X, Y, or Z, will be all of the X, Y, or Z components of the spatial harmonics. And these correspond to the magnetic field component of our spatial harmonics. The S's contain the amplitudes of the electric fields of those same spatial harmonics. Then our convolution matrix is no longer diagonal or banded, and it becomes a full matrix. And a lot of times we'll hear this called a Toeplitz matrix, but in fact it only has Toeplitz symmetry for one-dimensional systems. As soon as we move to 2 and 3 dimensions, it does not truly have Toeplitz symmetry. So let's look at how we might interpret our column vectors, the field amplitudes. So we have S is a column vector of all the amplitudes of our plane wave terms. So we'll draw all of our plane wave terms, and each one of these is the complex amplitude of one of these plane waves. And that's it. So if we added all these together, we'd have some strange field. It would be periodic, and it would be trucking along left to right. So that's the meaning of the weights in S. We can't look at those and see the field. In fact, we have to multiply those by plane waves and add up all of the plane waves to reconstruct what the field looks like. So if we apply this same conversion to matrix form for each one of our 6 of Maxwell's equations in Fourier space, we end up here. So this is really the useful place where we begin any kind of numerical method. And they're pretty simple. We can look at the original equations and see Maxwell's equations in here. The thing to remember that's different before, when we were in real space, these bold epsilons were diagonal matrices, doing point-by-point multiplications. Since we are in Fourier space, these are not the same matrices. These are now convolution matrices. The same goes for mu. These are convolution matrices. They're full matrices. So this is a very confusing part. How do we construct these convolution matrices? We are literally doing a 3-dimensional convolution in Fourier space, which can be very confusing. So I want to try to give you a feel of what these look like and then step you through the code for building them. To calculate the coefficients, we have this equation, which comes from the theory of complex Fourier series. Now, we could do a triple integration for every single coefficient that we want, but it turns out for cubic, tetragonal, and orthorhombic symmetries, we can calculate those coefficients with a multi-dimensional fast Fourier transform. So let's say we have a 2-dimensional problem. We have a unit cell here, so we would have an array of triangles, a square array of triangles. If we perform a 2-dimensional FFT, this is the FFT, and notice we have this little tiny bit of something in the middle. And if we zoom in on that, it looks like this. And these are our Fourier coefficients. The center one is the 0-order coefficient and is the DC value, or the average value, of what we had in our original function. And as we go outward, we see our higher order spatial harmonics. But the numbers in here are these amplitudes A that we would have calculated if we did this brute force integral method. It's just that this would take a very long time and be very inefficient, whereas the FFT is very fast and very efficient. So we just FFT the unit cell, and as long as it has cubic, tetragonal, orthorhombic symmetry, we get the Fourier coefficients. Another thing we really need to address is how many points do we need in that original grid that we FFT in order to get accurate Fourier coefficients, because we're not doing it analytically and we need to look at a convergence thing. So let's look at if we Fourier transform just a simple square wave. And we have red and blue lines here which represent the real and imaginary part of the 0-order Fourier coefficient, 1st order, 2nd order, 3rd order. And if we look at these, we see they're changing rapidly. And they really don't start to converge to a constant value until we get up to 200-300 points on our real space grid. And we can look at another function, a little asymmetric sawtooth, if you will, but the same basic conclusion. We need at least a few hundred points on the grid, and that's the conclusion. When we were doing finite difference frequency domain, we were using 20, 30, 40 points. In order to calculate Fourier coefficients, we need many hundred on the grid, so 256, 512, those types of numbers. And that's to ensure that we get accurate Fourier coefficients. Now, as soon as we calculate those Fourier coefficients, we can throw out those real space grids, even though they have a lot of points, so they won't take up a lot of memory if we get rid of them. We have 2 convolution matrices to construct, one for the permeability and one for the permittivity. So we have this picture in mind. Bold letter for a convolution matrix. This is going to be a big, bad, ugly square matrix, but we're going to think of filling this in one row at a time. 1st row, 2nd row, 3rd row, 4th row, whatever row this is, and so on. So for each row, the rule that we use to fill it in, we have to go back to this triple summation. And it's from this. This tells us how to fill it in, and I'll step you through that in just a minute. So given indices P, Q, and R, what row are we actually in? Well, here's how we would calculate it. We're going to raster first along P, then Q, then R. So we have an R minus 1 times P and Q, Q minus 1 times capital P, and then lowercase p. So given some combination of PQR, that tells us which row we're in. So what to come away from this slide is we're filling in this convolution matrix one row at a time, and we look at that triple summation to learn how to fill in that row. So here's how we'll start our MATLAB code. We're going to come up with a function called convmat, meaning convolution matrix. I just didn't want to spell it all out, I guess. But we're going to write our code in a way that we could call this one of three ways. If we just have a one-dimensional problem, we only need spatial harmonics along one dimension. If we have a two-dimensional problem, like the triangle on a previous slide, we need spatial harmonics along two dimensions. And for 3D problems, we need spatial harmonics along three dimensions. And we only live in a three-dimensional world, so we don't need to go any higher. So we'll declare the function with inputs A, P, Q, and R. The first thing we're going to do is look at the size of A. This is the thing that we're going to Fourier transform. So we extract the size of the grid. Now we're going to handle the input arguments. It may be that we only provided it A and P, or maybe A, P, and Q, or maybe all four input arguments. So we use this built-in function in MATLAB called nargin. That's number of input arguments. If the number of input arguments is just 2, meaning the user has only given A and P, it's a one-dimensional problem, we'll just set Q and R equal to 1. So we're only going to use one harmonic in the uniform directions. If the number of input arguments is 3, that means the user has given us A, P, and Q. We just need to set R equal to 1 because that's the uniform dimension. And if it's 4 or whatever else, we have all the input arguments coming in properly defined, and we don't have to do anything else. So from this point forward, we're going to treat everything as if it is a three-dimensional problem, but that'll reduce down to 2 or 1 just fine because we set Q and R to 1 as needed. So the first step in this is to calculate the actual Fourier coefficients. The first thing I like to do is compute the indices of these Fourier coefficients. So the total number of spatial harmonics will be P, Q, R, and we will set up arrays that go from minus P over 2 all the way up to positive P over 2, and this will pass through 0. So if P comes in, capital P comes in being 11, little p will go from minus 5 up to positive 5, as an example. So now we have these 1D arrays describing our indices. Next, we actually compute the Fourier coefficients. As I mentioned, it's an FFT. We don't know whether we're Fourier transforming a 1, 2, or 3 dimensions, so we use the built-in MATLAB function FFTN, which is an n-dimensional FFT. In fact, A could be 12-dimensional, and this would Fourier transform each dimension. So we will Fourier transform each dimension, even though A could be a 1D, 2D, or 3D array for our code. We will FFT shift that in order to place the zero-order harmonic right in the middle of our new matrix A, which is now the Fourier transform. And because of the way MATLAB scales things, we have to divide by the number of points in A. And we know the size, it's nx times ny times nz. So now A is properly scaled and contains the exact Fourier coefficients that we need. The next thing we want to do, we want to be able to locate the zero-order harmonic within the matrix A. And so that's how we do it. P0, Q0, and R0 are the indices in the three-dimensional array A of the zero-order harmonic. And the way we're doing this, 1 plus floor nx over 2, this actually handles the case whether nx, ny, and nz are odd or even or in any combination. This P0, Q0, R0 will always take us to the zero-order harmonic. It's very important to know where that is because all the other harmonics are located relative to that. So now we're going to start our loop to fill in this matrix. Well, we already said we're going to look at this from the perspective of filling in rows. We'll fill in the first row, fill in the second row, third row, fourth row, and so on. We're going to work our way down, and the row is going to go 1, 2, 3. So I like to set up a triple loop that iterate over P, Q, and R. And once we're inside, we calculate which row we're in. So this parameter row is going to go 1, 2, 3, 4, 5, 6, and all the way through however many spatial harmonics we have. So all this loop does is take us downward in the convolution matrix and tell us which row we need to fill in. So if we need to talk about the code that actually fills it in, all this code is doing is locating the row. We're working our way down the convolution matrix. So within the row, we need to locate columns. And in fact, we'll work our way left to right inside each row. So we have another combination P, Q, and R telling us which column we're in. And we want to calculate some integer, COL for column, that will go 1, 2, 3, 4, 5, 6, all the way across the convolution matrix. So we set up another triple loop, iterating over P, Q, and R for columns. Before our triple loop was over the row. We're going down in the matrix. Here we're going left to right through the columns of the matrix. So this parameter, this scalar number column, inside this triple loop will go 1, 2, 3, 4, 5, working left to right across the convolution matrix. So row and column now, we know the location of where we want to put the next number inside the convolution matrix. So the question is, what number do we put in there? That's where this triple summation comes from. So we want to calculate the indices that we need to grab the number from inside that A matrix where we did our FFT. And so to calculate what these are, we need to look at the indices on A here. So we need a P minus a P prime. So that's exactly what we do. P is our indices, P row minus P column. So this is essentially P prime, because this is talking about P columns, and the prime indices are stepping left to right through the matrix. And this is P row. This is stepping down. So this is P, and this is P prime. Likewise, where is the Q index in the FFT? It's Q minus Q prime. And then R in the FFT is R minus R prime. So in fact, we now know where we're going to get the number from, and we know where we're going to put it. And so we have one last thing to do. We're going to construct our convolution matrix C. We're going to put the number in row column. What number do we want? It comes from the A matrix, and we're going to give it these indices that we just calculated above. However, it's all relative to the position of the zero order harmonic, and that's where we add in our P naught, Q naught, and R naught. So that's it. This double triple loop constructs the convolution matrix and puts all the numbers in that matrix C. So here's what the convolution matrices look like. Let's say we start off with a unit cell that looks like this. It's an array of air holes and a bunch of a big dielectric background. So we FFT this, build our convolution matrix, and here's what we get. We notice the largest numbers are centered around the center diagonal. That's very, very typical. And then they drift off to usually very, very small numbers out here. The reason this happens, it means that spatial harmonics tend to couple energy to spatial harmonics that have a similar indice. We tend not to see the -7 order spatial harmonic exchanging energy too much with the A2 harmonic. Usually it only exchanges energy with local harmonics that have a similar indice, which means the big numbers are around the center diagonal. As we go off, we're talking about very disparate, coupling between very disparate spatial harmonics. So that's what our convolution matrix looks like. It is full, albeit the numbers get smaller as we get off the diagonal. So what happens if our device is perfectly homogeneous? Well, it turns out we don't have to do any of the FFT stuff. The convolution matrix of something that is homogeneous is just a diagonal matrix. It has all zeros out here, all zeros down here, but something other than 0 going down the diagonal. And in fact, what is going down the diagonal is whatever the function value was over here. So if we have all 9s in our grid, we will have all 9s going down the diagonal. What this tells us is that if it's homogeneous, there's nothing to cause coupling between different spatial harmonics. So we only have numbers going down the diagonal, meaning the harmonics are only coupled to themselves. They don't exchange energy. If there's any kind of modulation, any kind of structure over in our unit cell, that's when the spatial harmonics exchange energy and we get numbers off the diagonal in the convolution matrix. So in this case, we don't need to construct a convolution matrix if it's a homogeneous layer. We just take the scalar epsilon naught and multiply it by the identity matrix, and that is our convolution matrix for a homogeneous device. Some final notes. We actually constructed here an extremely powerful code. You can use this for 1 dimension, 2 dimensions, 3 dimensions, and in fact, if you ever get to 4 or 5 dimensions, hopefully it's pretty obvious how to modify the code to do that. So we can construct convolution matrices for 1, 2, and 3D convolution. That's pretty cool. For 1D devices, we only retain spatial harmonics along P, and we will set Q and R equal to 1. 2D devices will have a P and a Q. We'll set R to 1. In 3D devices, we have both a PQ and an R. What to remember though, we use the FFT to calculate the Fourier coefficients. That means we can only use that code to calculate convolution matrices for cubic, tetragonal, and orthorhombic symmetries. Any other crystal symmetry, we have to go back and resort to the brute force integrations. Also remember, if we have a homogeneous material, we don't even have to go through the whole convolution matrix thing, although we could, but the convolution matrices are diagonal, and the number going down the diagonal is whatever value was in that original real space grid that we Fourier transforms. So another lesson we can come away, if you have a device that's periodic, if it happens to have a uniform direction, maybe it's the y direction that's uniform, then we would just set q equal to 1. If the x direction is uniform, we'd set p equal to 1 and just use harmonics along q. This MATLAB code I just stepped you through can handle any of those cases just fine. On to our next topic called fast Fourier factorization, which is a relatively new topic in Fourier space. It's probably maybe 15 years old now, something like that. So let's say we have the product of two functions, f and g, and then we set the product equal to h. And let f and g both be periodic with the same period. So that's important. They can't have different periods, they're the same period. But if each one of these are periodic individually, h will also be periodic. So in fact, we can expand each one of these into its own little Fourier series. So that's exactly what we do. Here's the Fourier series for f, here's the Fourier series for g, and here's the Fourier series for h. Now, this equation is valid. It holds. There's no problems. However, notice there's an infinite number of terms in these Fourier series. That's why there's no problems. As soon as we go with finite number of terms, we run into problems with this. And this is where fast Fourier factorization comes in. So if we have a finite number of terms, let's call that number of terms m. We'll give each one m terms. In fact, we have 2m plus 1 terms if we do it this way. So there's 4 cases where we need to think about what happens. The first one, if f and g are continuous everywhere, then so will h be continuous. In fact, there's no problems with that. Another case, suppose f or g has a step discontinuity somewhere, but there's no step discontinuities of f and g at the same time. It's only one or the other that would have a step discontinuity. We'll call that case 2. Case 3, f and g have a step discontinuity at the same point. However, their product, f times g, is continuous. So that function h would be continuous, since the product of f and g is continuous. And then we have a fourth case where f and g have a step discontinuity, but not even their product is continuous. So the h function is also discontinuous at that discontinuity. So when we retain just a finite number of terms, it turns out it's cases 3 and 4 that have problems. And the way to word this is we get very slow convergence for cases 3 and 4, which is when f and g have a step discontinuity at the same time. Now the good news is we can fix case 3. The bad news is we can't fix case number 4. And a little bit of more news. Fortunately, case number 4 never arises in electromagnetics. So that's good. So here's the fix. If we Fourier transform that according to what we talked about previously, we would have a convolution matrix in F. We would have all the Fourier coefficients of G here and all the Fourier coefficients of H here. But this would be the big square convolution matrix. But let's say we're in case 3. F and G have a step discontinuity at the same point, but their product is continuous, so H is continuous. We get slow convergence though, but what happens if we take F and move it over to the other side of the equation? So now we have G equals 1 over F times H. Well, if F has a step discontinuity, so does 1 over F. But H is continuous, so in fact this product is now case number 2, which does not have any problems. And this sitting all by itself, not multiplying another function, is also case 2, no problems. So we will form the convolution matrix with the inverse of F. Now that we have this convolution matrix, we can bring it back over to the other side. And in fact, the fix to this now is we take the reciprocal of F, construct a convolution matrix, and then invert that convolution matrix. So we did a strange kind of double inverse thing. But now this has proper convergence. Everything converges at the same rate. And this is called fast Fourier factorization. So let's look at this convergence problem. We have the blue line, which is F, the red line, which is G, and the green line is H, so it's the product of F and G. And what we see is our two functions, F and G, everything's continuous here, even H. So no real problems. So now, let's look at the convergence of H. So here is the Fourier transform of H, or we're reconstructing the function through the Fourier transform with a limited number of harmonics, 1 harmonic. And this is the reconstructed function limiting the harmonics of F times G, if you will. But what we can see at 2 harmonics, and by the time we get to 3, they're really matching. 3 harmonics is not bad, so we don't see really a convergence issue with case 1. If we look at case 2, we see that G has a step discontinuity, but F is continuous. So in fact, so is H. And we see by the time we get to even just 7 harmonics, they're looking pretty similar. So it is a little slower convergence here, but still really not bad. Now we're going to look at the case where both F and G have a step discontinuity, but their product does not. So H is still continuous. Well, as promised, we have a very bad convergence issue. We see that the limited number of series Fourier expansion, the green line, converges really fast, but the one constructed from F and G converges very slowly. We have 31 harmonics, and we still have a pretty sloppy problem here. Well, now look at case 4. Again, it's still very, very different, considering we're using 31 harmonics, 31 terms. Well, now let's build in fast Fourier factorization, and boom, it converges right away. We get very, very fast convergence. Now, these two cases, this doesn't mean that they're never going to converge, although there is some literature saying that sometimes they never do converge, but they do get better, and we can fix it. So the problem with not implementing fast Fourier factorization is that convergence is slow. That doesn't mean it doesn't converge. It just means it's going to be slow, and we can speed this up with fast Fourier factorization. So how do we do this? And where does it arise? Well, we have an epsilon times an E. We have two boundary conditions that we reviewed, I think, in the second lecture. The tangential component of E is continuous across the interface. So if we have an interface, epsilon is discontinuous, but the tangential component of E is continuous. So in fact, that's case 2, not a problem. Well, we also have to look at the normal component of E. We have epsilon times E equals epsilon times E. So in fact, while the normal component of E is discontinuous across the interface, the product of epsilon times the normal component of E is continuous across the interface. So they'll both have a step discontinuity, but their product is continuous, which is why this is fixable. That puts us into case 3. So how do we build this into Maxwell's equations? Well, we have an epsilon times an S. We can decompose S into tangential and perpendicular components. Well, now we can multiply this out, and we have an epsilon multiplying S tangential plus epsilon multiplying S perpendicular. Well, now the fact that we've separated the perpendicular and parallel lets us potentially do something different to these two epsilon matrices. So let's just call it epsilon r tangential and epsilon r perpendicular. Right now they're the same thing, but we might want to modify these. So if we have a discontinuity, our epsilon will be discontinuous, but S will be continuous. So there's no problems here. That's case 2. We don't need to do anything. Over here, if we have a discontinuity, epsilon will be discontinuous, and also the normal component will be discontinuous. So we have the product of two discontinuous functions where they have their discontinuity at the same point, but the product is continuous. That puts us in case 3, which has very slow convergence but is fixable with fast Fourier factorization. So in fact, what we'll do is we'll take this matrix, we'll invert it, construct the convolution matrix from the inverse of that permittivity, and then invert the convolution matrix. And now we have a new equation where we've incorporated fast Fourier factorization and fixed the slow convergence problem. Well, here's the tough part of this. How do we know what the tangential and normal component is? We could have a very strange device, and we have to somehow know normal and tangential components. So there's a lot behind this, but suffice to say that we can construct something called a normal vector field. And what we're looking at in these pictures are this U shape is some kind of dielectric structure. What we want is a vector field that is always normal to the interfaces. And if we construct it, in this case, it looks like this. This maybe is not perfect, but it's very, very good. Here's another example where we have some strange distribution of dielectrics. And we need some field that is always perpendicular to the interface. We can see it gets messed up here, but for the most part, we know where it's perpendicular. And we can use this to decompose the field into normal and perpendicular components, normal and parallel components. So this field of vectors we call the normal field. That's not easy to calculate. Sometimes we can do what is essentially an electrostatic model, and fields tend to be normal to interfaces there. There's some other techniques for doing that. I don't want to go down the road of teaching that, but I did reference one paper here that talks about that. But somehow we're going to come away with this normal vector field. So here's how we tie it all together. We have our ordinary convolution matrix. We also have a convolution matrix that we construct from the reciprocal of the dielectric function and then take the inverse of that. We also have another big square matrix that we derive from our normal vector field. And we tie this all together and essentially come away with a new permittivity matrix that takes all this into account. A lot of details here I'm skipping. I just want to give you a flavor of what's happening here. So let's talk about the consequences and the benefits of Fourier space. So let's say we have a device that is a triangle. The top row in here is this triangle represented on a real space grid. And I might argue it takes a lot of points on a grid, 31 by 31, before this looks like a pretty good triangle. Well, if we put this in Fourier space and we construct it with an increasing number of spatial harmonics, I would argue that it takes fewer harmonics to come up with something that looks pretty triangular. If you notice, if we compare it to this triangle, there's a huge staircase approximation. Not so bad here. So the whole thing is, if our structure is periodic, it is probably more efficient to model it in Fourier space because we can get away with many fewer spatial harmonics than we could get away with points on a real space grid. So that's the benefit of it. Now there's some drawbacks. We're looking kind of top down on this triangle function. If we only use one harmonic, we really just have the DC value. And some people might call this effective medium theory. And in fact, a lot of work has gone into this. And this actually has some value. But let's look at, we'll use 3 by 3 harmonics. That really doesn't look a whole lot like a triangle. 5 by 5, we're starting to see a triangle. Maybe not too bad, but the edges are definitely blurred. They're not crisp. 7 by 7, we're getting a little bit crisper edges. And 11 by 11, even crisper. And by the time we get to 81 by 81 harmonics, it's essentially looking like a perfect triangle again. So the conclusion here is, when you use too few harmonics, it is essentially blurring your device. And your model will actually think the device is blurred and model it that way. Another consequence of doing things in Fourier space, we have this thing called Gibbs phenomenon. And let's say we have a square wave, we Fourier transform that into a Fourier series, but we only retain a certain number of terms. We know it won't represent that square wave perfectly, but it turns out we get these overshoots. And this overshoot here is called Gibbs phenomenon. It turns out the magnitude of that overshoot stays the same, no matter how many harmonics we use, no matter how many terms in the Fourier series we use, the magnitude of this overshoot stays the same. And in fact, we can quantify that pretty easily. The only thing that does happen when you increase a number of harmonics is they get skinnier. And if you have dielectric structures, that becomes a little bit less significant. If you're modeling things with high index or even metals, that little spike looks like a metal there. It becomes significant. But no matter what, your model is going to work as if those dielectric spikes are there. So what would the device look like in Fourier space with Gibbs phenomenon? Notice we have these overshoots here. You're going to be modeling these devices as if these overshoots are there, and they don't go away, but they do get skinnier. So it's because of Gibbs phenomenon that I think rigorous coupled wave analysis, plane wave expansion method, Fourier type space methods are best applied to things with low to moderate index contrast. When you get to high contrast in metals, are they more efficient than the real space methods? Some people still think so. Some people still use them. You can definitely get good answers, but the convergence is so slow. We need so many spatial harmonics. I'm not convinced it's more efficient than a real space method. So that's the full story to Maxwell's equations in Fourier space. We expanded the field into this plane wave basis. We substituted those expansions into Maxwell's equations. We turned our algebra crank, and we ended up with Maxwell's equations in Fourier space. We then realized we have to write all those equations for every PQR combination, every spatial harmonic in the expansion, and we could write that huge set of equations in matrix form, which we did. Now, we didn't talk about how to solve it. That's coming in following lectures, but hopefully we understand now Maxwell's equations in Fourier space and how to put them in matrix form, and also some of the consequences of being in Fourier space. We can get away with fewer spatial harmonics, smaller matrices, But if we use too few, it tends to blur the device, and we also have Gibbs phenomenon to combat. So that's it.